So who am I to talk to you today about TensorFlow? I am, as Joe said, I'm a freelancing data scientist. I'm ex-Microsoft, so I used to be a data solution architect and decided to go now and help companies to solve their problems. My background is in machine learning. I did my master's degree in machine learning, although it was so long time ago. It wasn't called machine learning back then. It was called data mining. And I have a strong programmistic background. And when I was doing my master's and then when I started my PhD, my mentor told me this thing when I was choosing my field. Don't do this neural network stuff. They're so niche. No one is using it. There are like few people in some research areas, and they are just wasting their time. That's what I heard. Well, to be honest, they are probably kicking themselves too. But at that time, seriously, those neural networks weren't a thing. So if you want to contact me, I'm the only person in the whole world named like this. So wherever channel you find me, that's me. And I own all the domains with combinations of my name and surname. So what am I going to talk to you today, but we'll also show you some stuff, is basically TensorFlow. A little bit what deep learning is, and then straight to demos. I will show you, well, hopefully 6 demos, but we only have 45 minutes. So if I don't show you all of the demos, or if I skip through some of them because we have time limits, I have a good news for you. There is this amazing platform called Katacoda, and all of those demos will be there. I mean, they are already there. And it's not just, GitHub repository. It's an actual environment that you can run, experiment, and do the exactly same thing that I will be doing now. So if you're not that interested, you can go to some other talks and then just replay. But no, please stay. So what is deep learning? Or maybe before we go to that, who has ever heard of deep learning? Who has ever used a little bit of a deep learning? Okay, who has ever used TensorFlow? Okay. What are you guys doing here? So what is deep learning? Who can tell me? Come on. You guys are screwed because you have to, look at me. You cannot just look around. Any ideas? There are no bad answers. There are so many answers in the internet. You can give me yours. What's deep learning? I won't talk to you anymore if you don't answer me. Come on, I gave you a robot. Tell me something. You, sir. What is deep learning? What do you think deep learning is? Yeah.
It's a large stack of model type structures that gives you an output for a defined input according to a certain goal.
So some technology that takes an input, gives you an output. But how do we use deep learning? Where do we use it? Image recognition, NLP, robots, right? So there was a great keynote today that we heard that deep learning and this AI stuff and deep learning is now passé. It still has its use, so don't lose hope. The best answer I've ever heard when I was giving a talk on deep learning was, deep learning is matrix multiplication. And this is a very valid answer if you think of all those GPUs and all the hype stuff. So I'm very excited about deep learning, AI, machine learning in general. And we are actually living now in very exciting times. We live in the future. And when I think of all those movies or books, when I was reading Harry Potter for the first time, I was really impressed with Hermione. And I also thought she's a very good hacker because she knew all of the commands. So all those spells in a software world, in our tech world, it actually reminded me of a tech. The book about magic reminded me of the tech. And yeah, that was the first time when I thought we are actually living in the times when technology is almost indistinguishable from magic. I'm saying almost because we have a lot of stuff to work on. So what about those neural networks that my mentor and advisor said that they are the niche thing? Why they are called neural networks? Because someone thought we could mimic the brain. And there are some entities there. There are neurons, there are connections between them, and there are so much stuff that we have no idea. I am not a neuroscientist, don't get me wrong. It's just, when you think of AI and deep learning in terms of, well, actually mimicking the brain, you're wrong. Neurons and connections, that's it. That's what we took from the brain. And sometimes some researchers are actually proving that, well, those artificial neural networks are kind of behaving like a brain, but it wasn't because we tried to mimic it. So what did we take from this brain analogy? We took math. We took something that we think is happening. So we have some neurons. Those circles are neurons. We call them sometimes cells, sometimes we call them units, and we connect them. This is the example of fully connected network. So we have 3 layers, the input one, the output one, the hidden one that is not really hidden because you can see it and access it. It is historically called hidden. And what is happening in this case is you're taking, let's say this neuron that is highlighted, you're taking all the inputs, you're multiplying them by some weights, then you're aggregating them, usually by summation. Then you put it through some activation function. And if you know a little bit, even a little bit about linear algebra, you know this is matrix multiplication. But as I told you, neural networks are not the new thing. If you could look at this timeline, the first one actually thought of mimicking the brain was in 40s. And this was the time when my thesis advisor told me not to do it. This is a very recent thing that they actually started to work. So what changed? What happened? What's different now that wasn't there for 60 years, 60, 70, almost 80? Yeah?
Huge amount of data and much more computing power.
Yeah, we have much more computer power, and we actually have big data. We live in a time when we have tons of data. Every company is gathering data. I go to companies very often, and what they want to do, we have this data, do something with it, predict the future from it. And we can do it now. Well, not in a creepy AI taking over the world way, but we can use this data. And we have a lot of computing power. We have the cloud. So from pennies sometimes, you can just run parallel computations and have amazing results. We have GPUs, TPUs, other PUs. So companies are now working on creating the hardware that will be great for us. And then we have libraries like Tensorflow. Tensorflow is not the only one. It wasn't the first, by no means. It wasn't even the first that was open sourced. But now it's winning the popularity contest. Google open sourced it, and now we can play with it, and it has a great community. So what was amazing with deep learning was it finally solved the biggest challenge of AI. Do you know what's the biggest challenge of AI? Distinguishing cats from dogs. So finally, when we have our computer vision task, we can do it. Because before, we had to put the hard rules there, like cats have pointy ears. But wait, some dogs have pointy ears. I have so many species of them, and now, because of deep learning and libraries like TensorFlow, we can finally do it. Okay. Let's go to the TensorFlow thing. The first sentence, build a computational graph. So what is the computational graph? Computational graph is a concept that is not just in TensorFlow, in many actually deep learning libraries, that is based on deferred execution. So first you're saying, I will be doing this, let's say, I'm taking m and x, I'm multiplying them, then I'm adding it to b, so I have y, and I can do some other stuff with it. While defining it, you're not doing any computation. You're just saying, define me this kind of an operation. And then, once you have a session that is running it, you can get the results. This computational graph can be used with different input data. It can be very, very complex. This is an example of tensor board, so it doesn't have to be very simple. It's usually not very simple, and so you have tools like TensorBoard to visualize it and see how it happens. This very, very simple concept of deferred running is very powerful. So let me show you the demo and first concepts of TensorFlow. So this is my course on Katacoda. Let's start scenario. So basically, whatever I will be telling you now, it's here, so you can then run it later. So I'll run Python, and I'll import TensorFlow. The first thing is so I'm explaining what's computational graph. We'll build something that is adding two numbers. So I have input 1 and input 2. So those are two constants. So I have a constant that I define as 2 and another that is of 5. But if I print them, it tells me not 2 and 5. It tells me that I just printed two constances, because constant, even though I applied it with some specific number, is still a tensor, it's still a part of computational graph. To run it, I need to run a session, and I will show you that in a second. Can you see the code properly? Okay. So I'll run the session then, and now I'm printing it with session run. And now I can see 2 and 5. So the concept of deferred evaluation. So let's build this adding thing. So I'm adding those two constants. And again, if I print just the added node, it will say it's a tensor. But when I run it within a session, it will print the result of computation. So you can see, first it's a tensor, and then it's a 7, because when you add 2 and 5, it's 7, right? It's higher math. So constants are easy, and you get the feeling how to add. So you can imagine you can multiply, divide, etc., etc., etc. Okay, let's use this concept to define the adding and then use it with different inputs. So first of all, you need to say, I want to have two placeholders. Placeholder is placeholder that will be filled with the value at the moment of evaluation. So again, I will define adding. Now I used just a plus symbol, which is also doable in TensorFlow. And to actually run it, I need to say, you can see it, I need to say for placeholder 1, use the value 2. For placeholder 2, use the value 5. So in the second example, I used float value. And for the third example, I actually used even arrays. So you can add arrays. So let's see how does it work. So 2 and 5 gives you 7, 4.7, 6, and 10. So imagine you have a very complicated graph, like very complicated. You don't have to redefine it over and over again if you just want to feed it with different input values. And then variables. Variables are something that is tricky first when you encounter TensorFlow. And I think TensorFlow people are just treating them as something that is understandable. For me, it wasn't at first. Variable for me, when I'm writing a code, it's a variable. It's not something that, in case of TensorFlow, that you're actually optimizing, that you're changing when you're running your deep learning or any kind of a training process. But the definition is very simple. We're just saying, well, let's say I'm putting the x and y, and I will be optimizing the function a times x plus b. And I'm creating two variables. So what I want to do, I want to create a linear model, and then I want to say, well, actually, this model may not be the best. I'll show you the picture here. So I think I've run it with the green line, and I want it to adjust to those points. This thing may not be optimized, so I want to change those variables A and B. And to do this, you can just use assign. Oh, sorry. Yeah. You can just use assign stuff. Oh, this is something that you are not learning in the first tutorials for TensorFlow, because nobody is actually using assign for variables, because we have TensorFlow that is using optimizers and changing our variables inside of some functions. So TensorFlow gives you a lot of abstraction. But if you want to build your own algorithm that is changing and tuning those variables, you can using this assign function. So if you want more details and play with this line to adjust it, go to this tutorial, go to this scenario, and have a play yourself. So this was a very, very simple example how to build a computational graph. And the next example I will show you, if something is shown, okay, will be for a classification task. So it's much less abstract, much more concrete. If you've ever encountered deep learning, this data set is one of like a hello world examples. So we have handwritten digits, and we want to classify them for 10 classes, for digits from 0 to 9. So we will build a network and then try to classify it. Every image from this data set is 28 by 28 pixels, so as an input, we'll just flatten it. And for the training process, there is this thing, very weird thing with deep learning. It's like almost never, even with the tutorials, you're using the whole data set to train. Or not even using the whole training set to train. You're using batches. Why you're using batches? Because it gets to the solution much quicker, because it doesn't have to tune all of the parameters based on every example. And once we talked about big data and you have a big training set, you can imagine how time-consuming it is. Splitting it into batches gives you, well, even better sometimes results, but with the time that is much more limited. So the first thing I will show you is how to build one layer network. So we only have an output layer. We have this matrix multiplication. And I will use TensorFlow computational graph to tune the variables. The variables are weights and biases, so W and B. So the second demo is basically okay. I'm importing TensorFlow. I will shut it and make it a little bit bigger. I'm importing TensorFlow and I'm reading the data. TensorFlow is so kind that it has a data set just built in. So the second thing I want to do is to put some variables, and those variables are different than TensorFlow variables. Those are actual programmatic variables. And then I'll train the data. So how do I train the data? I'm creating the placeholders. So you can see here that my placeholders will be my training data and my labels. Then I'm creating network variables. So as I told you, weights and biases will be my variables. I'm putting them in a proper shape, and then I'm creating my output layer. My output layer is just basically this matmul, means multiply those matrices and add bias. So I have my output from my network, and now I need to define something that is called loss function. For those of you that are not familiar with what loss function is, it's a very common technique in any machine learning algorithm, that you're swapping machine learning problem to the optimization problem. So you'll find some kind of a function and say, I want this value to be minimal, and I want it to adjust my variables to be optimal. So our loss function is something that's called cross entropy. Don't worry about what it is. Basically, it's taking the values that my network is outputting, the true labels, comparing them, and trying to minimize the difference. It's a little bit more complicated in terms of the exact equation, but that's the gist. So I said, use the cross entropy, get my labels, the true values, and get my output that my neural network is there. So this is my loss function. And then I'm saying, use gradient descent optimizer and minimize my function. So if you've ever learned about stuff like backpropagation, gradient descent, stochastic gradient descent with momentum, Adam optimizer, you don't have to now. You can just use the function that is provided by TensorFlow. And the last thing is, of course, I also added some statistics. The last thing is to run the training. So to run the training, I'm starting a session, and then in few steps, I'm running the training step. And I'm giving my training step the input data from batches instead of from the whole data set. The last thing is I want to just display some results. So let's run it. So it extracted stuff, and this is my accuracy at the end. It's not the best, but it's not horrible. You could do much better with deep learning and TensorFlow. Okay. Okay, not okay? Okay. Second sentence, once we have our computational graph, is to pick our level of abstraction. And you've seen a little bit of it, because if you have never seen TensorFlow before, and you've just seen what I've shown you, it could be a little bit confusing. It could be confusing if you've heard about deep learning, but you don't know TensorFlow. So sometimes you want to tweak the optimization algorithm. Sometimes you want to build your actual layer. And sometimes you want to use something that is very, very high level. So let's start with very, very high level. This is very high level machine learning supervised process. So we have some data, we read it, prepare it, clean it, and then we usually split it to the training and testing, and then we run the machine learning algorithm. It can be a neural network, can be something completely different. Then once we have our model, we can evaluate it. So TensorFlow allows us to actually do it. We will just say, I have this data, I want this split, I want this algorithm, train it. And this is where estimators are coming in. Estimators are fairly new. They have like few months now for TensorFlow, and you can use different ranges of algorithms. So you can see like they're like linear linear regression, and this list goes on and on and on if you go for this page. What I will show you is how to just build deep neural network classifier. And this time, I want another layer. This time I want input layer, and I want the hidden layer. The great thing about when you're building your own neural network is this hidden layer is not really hidden. But if you're using something that is wrapping it up, like estimators, it is hidden. You only have access to the output of the network, not to the specific elements at first, because there are ways how to do it. So what estimators are doing is you're defining the input, you're defining the labels, you're saying, fit this model, evaluate this model, predict new examples, and then you can even save it. So the third demo is doing exactly this. Well, this time I'll just show you the code. So what I just did is I'm again reading my data set, and then I'm saying, well, this will be my input data. So I want images from this data set, and I want labels, and I want labels to be treated like integers. And then this is my algorithm definition. So no variables, no weights, no biases, not saying nothing that says you need to get this input and connect it with the output. All I'm saying is take my feature columns, which basically takes the values from the data set, use hidden size, which I've put, I believe, on 1024. So I will have 1024 neurons in the hidden layer. Use label size, so the output layer will have 10 neurons, and use Adam optimizer. And that's it. And then what I'm saying is fit my classifier. And then once I have it, evaluate it, check the accuracy, and then if I have some new examples, predict them. So it's a very high level of using any classifier. If you change this class, the NN classifier, to some other class, like linear classifier or logistic regression classifier, it will work the same way. You will probably need some different parameters here, but that's basically it. I'm explaining a lot of stuff here. Again, it downloaded the data, and then it's just fitting it. Now we don't see the progress because I didn't put logging in place before we've seen it. And also, it takes more time because I put the hidden layer. So this is what we've got, 97%, 32%, and those are predictions in comparison on the proper labels. Okay. What if you want some control? You need to choose another abstraction layer. So let's say we want to build convolutional neural network. For those of you who don't know what convolutional neural network is, it's basically a way of using surroundings for the image. So convolution works in a way that goes like with patches and does stuff for the image. So at this time, when we have images, it will not flatten the images. It will work on the whole image, I mean, on the patches on the image. And what does it give you is to recognize like lines, like borders between stuff, and then after like another layer and another layer, this is the way how actually deep neural network work for computer vision. And if you want to, implement it by hand, it will give you a lot of fuss. I encourage you to do it, of course. This is the best way to learn how actually convolutional network work. But after some time, you will get bored and you will write your own framework. The good news is you don't have to. And TensorFlow is giving you few ways of doing and choosing your level of abstraction. Another thing is polling. This is a technique that is used very often with convolutional neural networks. And again, you can do this on your own, basically going through patches and taking either average or maximum value from your patch. But you don't have to because you have functions in TensorFlow that will do it. So you can imagine how to build like a deep neural network. We have two convolutional layers, then we need to flatten the results, and then there is another dense, fully connected layer, and then we can have output. And TensorFlow gives you a lot of ways to do it, well, with different packages. One is just TensorFlow neural network package, and another is layers. So I'll just show you very quickly how do they compare. Maybe I will even show you that in parallel. Oh, did I put estimators again? Okay. Let's do convolutional. And oh, yeah, because I always do it. Thank you. So this is the way. I will just show you how to build a convolutional network to define convolutional variable and biases with more controlled ways. So you have a lot of control. So you're defining variables the same way as you've defined it for the dense layer. So you have TensorFlow variable. And then you're building a convolutional network. So to build a convolutional network, you use tf.nn.conv2d. And then you're getting the input, you're getting the variables, then you need to decide what strides are, padding, and then add bias, and then you wrap it up, all of this with the rel function. It's still not the most complicated layer, but I'm starting to have a headache a little bit. In comparison, if you want to use higher API, like more abstract API, let's have a look at the TF layers. So this is TF layers, and it also has this function called conv2d. But what you don't have to do is you don't have to define any weights, any biases, because it does it inside. What you're doing is you're saying, build me the convolutional layer, use those inputs, then you're putting some parameters, filters, kernel side. You cannot avoid it because this is a convolutional layer, so the patch size can differ. The padding can differ. So those are parameters of the convolution itself, but it's much more compact. You're saying, use convolution on this image with those sizes, and then, at the end, wrap it up with the activation function. So all in one function. And then there are two approaches, or two reactions for those approaches. Is either you want to have more control and you want to know more what is happening inside of your neural network or anything from the programmistic point of view, or you're using more abstracted API. Choose. And with TensorFlow or with Google, this is a quotation. Don't blame me if this is no longer true, but what I heard, that Google says, everything is either not ready yet in Google or obsolete. So this is also a thing with TensorFlow. With TensorFlow, it's changing all the time, and people are adding different layers of abstractions. And sometimes when you have to do stuff over and over again, they just differ, like with numbers or with activation function or with some parameters. What are programmers doing? Building another library, building another abstraction. Because, you know, you can do it yourself, but then you can trust people in Google, people that are dedicated in Google, people that are in the community that are using it. So my third sentence was actually for you to choose your level of abstraction. So you could choose to use estimators, or you could choose to go a little bit down, use layers, or a little bit down, use neural networks, packages, or use train or contrib-learn, or some other libraries that they are working on and they will provide. So the third sentence, the last one, is to work with the community. And as I said, TensorFlow is not the only deep learning library. It's the library that is winning the popularity contest. And there are reasons for that. And this is also something that is a feedback loop. So once something is popular, once something is winning, especially in tech, especially with communities, People are working on it. People are improving it. And even if I think there was just a talk before that was comparing different frameworks, even if TensorFlow is not winning with some metrics, with many metrics it's not winning, and other frameworks are, there is a potential, there is not just a big hope. I think it's a safe bet to say, well, this will be eventually the best framework. Unless, something happens, something else will win popularity contest, and people will work on it. So TensorFlow is open source, as we know. Funnily enough, it wasn't open source from the beginning, right? It was something that people were working on in Google and then decided to open source. Some frameworks were open sourced from the beginning. And there are a lot of tutorials and ways to get started. We are actually with Katakoda, we are talking with Google people to make those tutorials more interactive on the website instead of just having like code snippets. But there is also a GitHub repository. And in the GitHub repository, if you just go and see the code and run this code, you have ready-to-use solutions. You have stuff like translations. You have stuff like image recognition. You have trained models that are saved, and the code that will pick those models up and do your thing. So again, another level of abstraction. You're just using this model, and someone already have trained it on some data. Just use it in your system. You can do it. It's open source, and you can use it in production systems. You want to change something? You can change something. And then there is this amazing project that's called Inception in TensorFlow. I will show you that in a second, why it's called Inception. This is actually the name of the architecture for deep learning. And I will show you how to use TensorFlow to just image classification without building a network, using somebody else's network, using TensorFlow network that is already there with all the parameters tuned. And sometimes this is all you want. You may not have resources or the knowledge or data scientists in-house, but there is something that already works. Why wouldn't you use it? So this is the Inception architecture, roughly. So you can see different layers, different stuff. And what I'm going to show you is a demo that is using this Inception thing in a Docker container, so you can upload any image to it and just run it to recognize the image. I think I can reset it now. Hang tight. Okay, so you have an Inception here. So first thing, we've rebuilt the Docker image, the official Docker image for Inception, because it served our purposes better. If you want to use exactly the same image, it's publicly available. So you can see how it's called. It's called katakoda/TensorFlow serving bash. So I have my image, and now I'm running it. Yeah, so now I will download the images. So I will download the image of grumpy cat, puppy dog, and a dog. So let me download them, all of them. And let's see, how does the network work? So first I'll try with the grumpy cat. So what does it say? Come on. Yes, okay. So it says, it's a Persian cat, Siamese cat, Tabby cat, lynx, or Egyptian cat. Definitely, this network needs some more training, right? It's not that bad. You will see that with the dog. So the puppy dog. Let's see what it says. It says, Beagle, English, Foxhound, Walker Hound, that's fine, and a tennis ball. It was a red ball, right? Okay. I don't have much hope for the dog. Yeah, not really. No, actually, it's fine, because it was It was trained on, I think it was ImageNet. So it's a set of standardized images that are there. You could run it. You could run your own network on it. So I don't know what was the deal with this tennis ball. But yeah, it even recognized the species correctly. So it's pretty impressive. And it's just a Docker container, something that, requires a lot of DevOps from you if you want to just be a data scientist. But there are people that are providing those images, that are providing all those libraries. So you could just pick it up and use it in your own system. So you don't even have to build your neural network. You don't even have to train it to be able to use TensorFlow. So that's it. We talked a little bit, well, I talked a little bit about deep learning. Then I walked you through the 3 sentences I think are defining TensorFlow. So first, building this computational graph if you want to build your algorithms. Second was to use your level of abstraction. So either use it as a black box or grayer box or very, very light gray box, or build everything from scratch, and then to work with the communities and to use and build on top of other people's work. So this is it. Those are my data. If you want to run all those demos, they're available for you publicly for free. Don't worry. And if you want to contact with me, as I said, just choose any channel you want. And thank you very much for coming.